Okay, scientific method. So we're talking about the STEM subjects. We've got science, technology, engineering, and mathematics. Mathematics. They're the STEM subjects. STEM. Science. Not going to go into the massive amount of history in science, but with relation to computers, what we're talking about in science is the empiricism and the study of computing and computer science. That is pushing forward hypotheses, and it goes through the scientific method, engineering theory, and there's loads of science out there, but the main science tied to my field of engineering is computer science. STEM, T is technology. From a branch of physics, a science, was born electrical, Faraday and all the rest of them, radios and all the things, so the E&E principles. The other E in E&E is electronics. And then along came the transistor, and you're able to take these discrete components like the resistor and the capacitor and things, and the old school valves and relays, and you turn them into micro. Mu is the representation in engineering for micro, so there's micro electronics. And in that is your CPUs, so all of your integrated circuits. That's the microelectronics. And what happens with regard to the technologies is that from programming a CPU using its microcode, we've got the 4 generations of language. Currently, it's well accepted that SQL and the things that are built on top of the technology as a software technology, SQL is the 4th generation language, and then we've got all the 4th generation tools and everything that encapsulate that. So the technology of software ultimately derives from the microcode in a microprocessor, from microelectronics, which has a whole lineage right back up to physics. So there's a whole field of study of products and technology. So we've got scientists, we've got technologists, people that are interested in the technology. You could argue that technicians and electricians and all the people that utilise tools fit into the technology. Anyway, engineering is about the fundamental principles based in the empiricism of science and using the technology to solve problems. So engineering is all about problems and their solutions. Now, there's a modern term called value. I say it's modern. Everyone used to go on about business value, and now you're talking about the value of the software product that you produce. But value isn't necessarily monetary. I mean, if a business is doing these things, it cares greatly about the monetary impact, but value also is other benefits as well. So I'm not going to go too deep into the business motivation models or strategy or anything like that. But ultimately, what engineering does is provides value by using the tools, mathematics, and science available to provide solutions. So it's going back to that unknown known. We don't necessarily deal with the unknown. The way that we deal with the unknown is that we can provide a solution for it. We can engineer a solution. So engineering really is all about innovative application of the other three subjects: the innovative application of maths, the innovative application of a technology, and the innovative joining together. So engineering is basically the whole of STEM, really. Now, comment on that is that science feeds into technology, technology feeds into engineering, mathematics. So they're all symbiotic, really, and they all feed off each other and into each other. Now, it's well known, if you've got 4 fields of study, right in the centre is where everything is driving forward somehow. They all move in different directions and you get influence with each other. So yeah, it's engineering. And then finally mathematics. It's dead boring, isn't it? But engineering ultimately uses applied mathematics and statistics and certain areas of maths. Whereas if you're just doing maths for maths' sake, and you're finding or rediscovering what nature knows, physics is very much mathematics, even though it's a science, and so on and so on and so on. And we could go down a massive rabbit hole here. So I think we'll leave it there. We know about STEM, and we know about, oh, we don't know everything. So there's loads of stuff out there in the universe that is unknown. The stuff that we just don't know. There's also stuff that we know we don't know it. So that's sort of in between knowing and unknowing, because we know it's unknown. Not that it's unknowable, although we've got no idea about it, but we know that we don't know. The other thing is that people generally have things locked up in their heads. It's tacit. Not going to cover the tacit explicit cycle, but it's out there. 1980s, great stuff done in the name of science, technology, engineering and mathematics. Tacit knowledge is in people's heads. So you don't know what they know. So that is called unknown knowns. Oh. So you've got people's information, it's all stuck in their heads, stuff that they know, knowledge. And then you've got explicit knowledge, and that is hopefully everything we know, which I think someone estimated is like 0.25% of everything. So there's a massive percentage of, was it dark matter and dark energy? So at best, we know 5% of everything, and we only know a little bit of that. That's what they're saying. So it's like 1/20th of what we actually is knowable at this moment in time. We know that dark energy or dark matter with our models exists. And that's currently making up 95% of everything. So there's 95% of everything we just don't know. We know we don't know it, but we don't know. And then the remaining 5% might be out there, don't know. But we're pretty certain that all the possibilities, it's something like 1/4% is if you write down absolutely everything. If you could write down absolutely everything that we know about language, you name it, write it down, make it explicit, it's about 0.25%. Scary, really, isn't it? So talking about STEM and known unknowns and all the rest of it, from science, we know that in order to prove something, it's got to have evidence. There's got to be data. Data is the plural of datum, by the way. So when we're talking about data, we're talking about the plural. Lots of datums. Just for interest. On that data, it needs to be sifted through, particularly in science and research and the like. It then becomes, through mathematics and engineering and everything else, information. A good example of that would be the shipping forecast. Take the shipping forecast. If you're actually listening to it, it doesn't make any sense. I mean, what's North Utsira backing? You know, what's gale warnings and everything else? You know, what is it relevance to? So all that gets broadcast is the data. If you know about what the shipping forecast actually is, it then stops being North Utsira backing 7, and then if it says 5 later, so if you had North Utsira 7 veering 4 later, that actually means quite a lot. It's actually stops being data when you know that North Utsira is an area of sea. If you know that the 7s or the numbers that are ever used are force, on the Beaufort scale. If you know that veering and backing or whatever, the next words are all about what the wind's doing. And then if it says later, soon, and things like that, they're actually the amount of time. So the shipping forecast is actually a massive amount of information that's sent. And if you're out in your boat somewhere, 20 miles offshore, and you worry about, force 7 or force 8 gale or whatever, so that's actually called a salesman's gale, is force 7. Anyway, you want to know what's happening later. And that's what the difference between data and information is. And then, once you know how your boat's going to perform in a force 7, whilst you're doing a bit of trawling or whatever, or you're just out round the cows or whatever, you're just on the sea. If you know that it's going to be bad later, perhaps you best head off home, hey? That would be wise. So from the broadcast, if you know where it's broadcast, it's on Radio 4 at such and such a time, so you've got lots of information already in order to tune in to the shipping forecast. So you've got the data, you then get the information, then you've got the knowledge to be able to decide to do something. So there's loads and loads and loads of information, of data. You then want to narrow that down, because you don't care about Viking and you don't care about Trafalgar. You care very much about North Utsira, because that's what the area of sea that you happen to be in, or you will be later. And then, now that you know all of that information, you've got your boat and everything else, so you've got loads of information points, tons and tons of data that's coming in. you can then decide what to do. So that's why we have the data, information, knowledge, wisdom triangle. So down at the bottom is all the data, then it's our information, and it's stuff we know, and then we can decide what to do. Apply a bit of wisdom. And that might feed back, because actually you don't know anything yet, so you might start there, the data's all rubbish and everything, so it becomes a feedback loop. So if we were to put a mathematical term on this, or maybe even electronics, black box or whatever, an f of x, it's all based on data, information, wisdom. So we also know that the output of that is going to feed back somehow. That's the difference between lean and agile. That's a conversation for another day. Okay. Engineering. Software. What is software? It is a complex sequence of instructions interpreted by a central processing unit. That's it. There's lots of different types, but ultimately software is a logical conclusion, and that logical conclusion is a sequence of instructions to a microprocessor that might have one or a number of peripherals connected that does things. So it's an abstracted way of managing complexity, and it's got more and more and more and more complicated as microelectronics has evolved. So what you can do with a CPU these days is much more than you could do with CPUs even 5 years ago. So, software, can it exist without hardware? In my opinion, my experience, no. Not software engineering. Without something for it to exist on, it doesn't exist, does it? It's ethereal. Or is it? What is it? You see, what it is it's all to do with the abstracted build, which we've covered that. We've covered the design, No, we haven't covered design yet, have we? Oh, right, I'll come back to that. Right, I'll make a note. Design. In fact, design. That's the first stage we're at in the engineering process, isn't it? So we need to design software that will run on some hardware. And in this particular problem that we're trying to solve, we need to design something. So software must be able to exist without hardware. Yeah. Software these days is many things to many people. Some people, the AI advocates, maintain that you don't need people to write software. AI can do it. Whereas I actually think that's missing the point. And here's why. It's accepted that there are 4 layers which we covered before. First generation, second generation, third generation, and fourth generation. So when we're talking about software and hardware, right at the very bottom here is the actual microcode that's interpreted by the microelectronics, the actual CPU itself, which, the instructions like load accumulator A, add accumulator A. Not going to go into the architectures of the computing systems right now, but ultimately that is the microcode. For any given CPU, you can go and see what they are. So back in days of yore, we had the 6800 Motorola CPU, and not going too much into computing or computer architectures, you had an accumulator, and you could load it by issuing the hexadecimal 86. Again, hexadecimal, that's something we need to go into, and binary and everything else, isn't it, I suppose? Anyway, you'd have a sequence of bytes that would, because it was an 8-bit processor, so these 8 bits were in a sequence, and your program would go through and go, load accumulator A, add it with accumulator B, and output it to a given memory address. Super fast. To actually achieve that, it's quite complicated. Anyway, I'm digressing. Then from the microcode, on top of that is an abstracted form. So this is your binary form. So they are the actual instructions that are loaded into memory that the CPU can fetch and read and execute. So this is definitely on the hardware target platform. In an operating system, they're called the binaries, such as like Windows or Linux, and they're stored in files. And those files are able to be loaded and executed. We'll go again into the mechanism of loading it from a hard disk into memory, and again, that's the architecture of the computing system, not necessarily the CPU, but yeah. So there's a load of electronics and microelectronics all here. So this microcode is really, really embedded. You might hear that term. Embedded in the electronics. So you'll hear about embedded software engineers, and what they're doing is they're right down at this sort of level. They care about the hardware and what it's doing and everything else. So one abstraction away from first generation languages was assembler. So what that was is, when I was talking about load accumulator A, you have these mnemonics. So load accumulator A with 86, and then you want to add it, and then you want to load accumulator B, or load the index register or whatever. So these assembler, it's abstracted one level up. So these were considered to be second generation languages. They were able to interpret these, and you write functions and call all the. It's like a wrapper around the abstraction, and these themselves, these were then called source files, which were compiled into the microcode, interpreted, whatever you want. Yeah. So there was a something that looked at the assembler, the load accumulator, and said, "Oh, that needs to be an 86," and would write 86 as a byte into a file, and so on and so on and so on. Then an example above assembler for a third generation language is the ubiquitous C. Kernighan and Ritchie, ANSI C, and all of those things. And it's still used today, C. From a safety perspective, we've got MISRA C, and others. The C++ as well, and all the programming languages. I would argue, probably I would argue that there's only one fourth generation language. That's SQL. There are probably others that I don't know about, the unknown knowns and known unknowns and all those things. But in my opinion, and my experience, SQL is the only fourth generation language out there. And this is where AI comes in. Not at this level, it's at this level. Because it can take in and interpret, from our DIKW, it works at the knowledge level. It doesn't know things. The neural net is, acting on probability, with a curve that, 80% of the problem, and the other 10% that's never going to happen, and the other 10% that's rare. So, your Pareto analysis and all that. But 80% of the time, AI is known to be reasonably accurate, and these other 10%, if you like, are hallucinations. It's a little bit less than that. It's more like 70%, I think, in the centre. So, instead of it being, down here at 10%, it's probably a little bit higher up. So whatever that area for 70% is, rather than 80%. Well, they're only going to get more accurate, I think. So really, AI sits here as a fourth generation language. So we can query it with natural language, and it joins the information with the things that it, knows, has been programmed, has learnt. So knowing comes from learning. So tacit within inside the AI that you generated from the data, that's then loaded and becomes information, which you sort of tell it on a probability basis. So the neural net then has knowledge, but it's really just a probability engine. Again, massive area of study, very, very pertinent today in 2026. So yeah, when I'm talking about programming a solution for this using AI, what I'm really doing is writing sophisticated SQL, but it's natural English language, and I'm pretty certain that other AIs will work in other languages. So when I'm talking about the language programming AI, what I'm actually talking about is the prompts. So you say, for a given base AI, I want this type of... So what you're programming in is in like a pseudo language, but that pseudo language is your entire language, and you might have to explain a few things. And using most AI like Gemini, you get this, you're able to store memories and things like that. So the notion of programming AI to me is the prompt at this moment in time. There are other things, but right now, at a prompt, when you're programming a language, at the SQL prompt, you'd type select star from customers. In C, you'd type, your main and all things. There's this format that you have to go through, and that is the same when programming AI. Anyway, we'll get into it, shall we? There are 4 basic stages to any engineering project, particularly software. There's a design stage, there's a build stage, testing, and then release. So this is your configuration management, which says all of this stuff together creates a package that we can send out to people. And this deployment mechanism, we're going to use GitHub. Can't spell. And the links for that are in the description below. That's the basic process.